Greetings, this is Professor Roman. Let's continue the lectures on linear algebra. The spectral theorem has told us that if we expect a linear operator to have a diagonal or a Schur block quasi-diagonal matrix representation, then the operator must be normal. So normality is clearly an important property, and we should explore it a little more carefully. What we know so far is that normality is invariant under unitary similarity. Two matrices that are unitarily similar are either both normal or neither one is. We also know that a linear operator tau is normal if and only if the unitary similarity class of matrices that represent tau under orthonormal bases is normal. Let's discuss some additional properties of normality. Assume that tau is a finite dimensional normal linear operator. Then tau star is also normal. If tau is invertible, then tau inverse is also normal. And p of tau is normal for any polynomial p of x over the base field. Also, if a subspace S of V is both tau invariant and tau star invariant, then the restriction of tau to the subspace is normal. It's not enough for the subspace to simply be tau invariant. It also has to be invariant under the adjoint of tau. We have this rather simple equation. Tau v inner product with tau w is the same as tau star v inner product with tau star w. This is a one-line proof. We just move tau across the comma to tau star, interchange it with tau, and then move the tau back, and we'll have tau stars in both positions. But in particular, if w is equal to v, we then know that the norm of tau v is equal to the norm of tau star v for all vectors, little v, which means that tau of v is 0 if and only if tau star of v is 0. And so tau and tau star have the same kernel. Therefore, they have the same nullity, which is the dimension of the kernel, and by the rank nullity theorem, they'll have the same rank. This is a very interesting property and characterizes a lot of the essence of being normal. The kernel of any power of tau, any positive power of tau, is the same as the kernel of tau. For any operator, if tau kills a vector v, so will any higher power of tau. So there is an inclusion going one way here for any operator. But if the operator is normal, then this becomes an equality, and that's going to have some interesting consequences. This is actually one of them. The minimal polynomial of a normal operator is a product of distinct, irreducible monic polynomials. As to the spectrum of tau star, when tau is normal, we have tau v equals lambda v if and only if tau star of v equals lambda bar v. or put differently, the spectrum of tau star can be gotten from the spectrum of tau by just taking complex conjugates of all the eigenvalues. Also, the eigenspaces are the same. So this is the eigenspace for tau star associated with lambda, and this is the eigenspace for tau associated with lambda bar. This is the eigenspace of tau associated with lambda. Same eigenspaces, same eigenvectors then, for tau star with respect to lambda bar and tau with respect to lambda. Here's another very important property. If S and T are tau invariant subspaces of V, and if the minimal polynomials of the restrictions are relatively prime, then the two subspaces are orthogonal. As a special case of that, if lambda and mu are distinct eigenvalues of tau, then the eigenspaces, being tau invariant subspaces whose minimal polynomials, x minus lambda and x minus mu, are relatively prime, they will be orthogonal. I left proof of part 1 for you. For part 2, this is a one-line. Let's go back here and look at part 2. If a subspace is both tau and tau star invariant, then the restriction is normal. So, excuse me, this is the restriction of tau to S star times the restriction of tau to S. The star can be moved inside, and so this is the restriction of tau star to S times the restriction of tau to S. That was an earlier theorem, theorem 6.6. And so we can interchange the restriction operation and the adjoint. Then these can be combined. It's tau star tau restricted to S. Now we can swap tau and tau star restricted to S, split them up, pull out the adjoint, sort of do the reverse of what we did in the first couple steps, and that shows that the restriction of tau to S is normal. You might need to study this a little bit. For part 3, which is this business here, and the norm and the kernel and rank, tau v inner product tau w, we can move tau over, tau star tau v w, then we can interchange tau and tau star, and then we can move the tau back and we'll have tau star v, tau star w. I said that before. Here it is in writing. This follows, and so as we already discussed, the kernels are the same, their nullities are the same, and so the ranks are equal. Part 4, which is one of the most interesting of the properties here, kernel of tau to the k is equal to the kernel of tau. Proof goes like this. First, we look at this operator, sigma, which is tau star tau. Sigma is self-adjoint. Sigma star is equal to tau star tau star, which is tau star tau, which is sigma. So sigma is equal to its own adjoint. Now there's a little bit of a, well, I hate to use the word trick, but it's let's say a key idea here that works. And there's different ways to actually implement this, but here's one of them. we're going to first verify that the property we're interested in, kernel of tau to the k equals kernel of tau, is true for sigma. Kernel of sigma to the k equals kernel of sigma. So suppose that sigma to the k v is 0. In other words, v is in the kernel of sigma to the k. That means that the inner product of sigma to the kv and sigma to the k minus 2v is 0. K here is at least 2. If k is 1, we're done. Now we can move one of the sigmas across the comma, and since sigma is self-adjoint, it doesn't change to the adjoint, or it is the adjoint, it's the same thing. So this becomes sigma to the k minus 1v inner product with itself, which is the square of the norm of sigma to the k minus 1v. If that's 0, then sigma to the k minus 1v is the 0 vector. So if v is in the kernel of sigma to the k, it's also in the kernel of sigma to the k minus 1. And we can repeat the argument, and v will be in the kernel of sigma to the k minus 2, k minus 3, all the way down to sigma. And so if the kth power of sigma kills v, so does sigma. If tau to the kv is 0, then sigma to the kv, which is tau star tau to the kv, because tau is normal, this is tau star to the k times tau to the k. Tau star and tau commute, so when you raise the product to the kth power, it's just each of these to the kth power multiplied together. But tau star of k is of v, tau to the k of v is 0, and so this whole expression is 0. So if tau to the k v is 0, sigma to the k v is also 0. Therefore, sigma v is 0. In other words, tau star tau of v is 0. And that implies that tau v must be 0. And I'll let you fill in that very short jump. Okay. So this is a proof. At least this part, for sure, is worth studying. So you get the picture here of what's going on. It's a little, as I said before, almost a trick. Okay, so for part 5, this is the statement that the minimal polynomial of a normal operator is a product of distinct distinct irreducible factors. They'll be either linear or quadratic, irreducible quadratic. Okay. So let's suppose that the minimal polynomial of tau can be written as p of x to the power e times q of x. And where p of x is irreducible, and we've pulled out p of x as many factors as we can. So p of x doesn't divide q of x. Okay. Then, of course, p of tau to the e, q of tau annihilates all of v. It's the minimal polynomial for tau. Now, however, p of tau is normal. That comes from part 1 of the theorem. And so part 4 says that if a power of a normal operator annihilates some vectors, the operator itself annihilates the vectors. So p of tau annihilates q of tau v. Therefore, p of tau, q of tau is the 0 operator. which implies that tau satisfies the polynomial p of x, q of x. But that polynomial has smaller degree than the minimal polynomial unless e is equal to 1. So the highest power of p of x that appears in the minimal polynomial is 1. In other words, every irreducible factor of the minimal polynomial appears only to the first power, and so the minimal polynomial is a product of distinct irreducible factors, linear and quadratic. Part 6 is, let me go back here. Part 6 is about the spectrum. Tau v equals lambda v if and only if tau star v equals lambda bar v. This becomes pretty easy to see if we rewrite this as tau minus lambda v is 0. In other words, it's this statement here. This is about kernels. From part 3, which I can go back here, we know that the kernel of an operator is the same as the kernel of the adjoint. So when we apply that to tau minus lambda, this kernel is the same as this kernel. When we take the adjoint of tau minus lambda, it's tau star minus lambda bar. Remember, adjoint is conjugate transpose, so we have a conjugate here. So then that means that this statement is the same as this statement for all vectors v, and so tau v equals lambda v if and only if tau star v equals lambda bar v. For part 7, we have two subspaces S and T, and their minimal polynomials are relatively prime. So let's say that tau restricted to S, that the restrictions of tau to those subspaces have minimal polynomials that are relatively prime. So let's say tau restricted to S has minimal polynomial p of x, tau restricted to the other subspace T has minimal polynomial q of x, p of x and q of x are relatively prime. We can use Bezo's identity, which implies that there are two polynomials a of x and b of x for which this equation holds. And so when we replace x by tau, we get the identity operator. Therefore, for any vector in the subspace S, call it little s, it's equal to iota times little x, iota is the identity, so it's equal to this operator times s, but p of tau kills s, and so we're only left with the second term. And similarly, for any little t in the subspace T, little t is equal to a of tau, p of tau, little t. Therefore, since tau is normal, we can do some shuffling. The inner product of s and t is, I just copy these two down here, and that can be, these operators can be shuffled around to produce this. Now p of tau star s is 0 because p of tau s was 0. Those kernels are the same. Same thing over here, we just get 0. So it would be useful to fill in the reason here that I can go from this one to this one, just for practice. finally, Part 8 is just a special case of Part 7. As I discussed earlier, the minimal polynomials in the situation are both linear and distinct, and therefore they're relatively prime. Monic, linear, and distinct. Now that we've examined the normal operators, there are, among the class of normal operators, two special subclasses, and we want to take a look at those. The self-adjoint operators. Obviously, if an operator is equal to its own adjoint, then it commutes with its adjoint. And the unitary operators, also known as isometries, and we've discussed those prior to this lecture. If an operator has the property that its adjoint is equal to its inverse, then it also has the property that it commutes with its adjoint, so it's normal. Here are the formal definitions. V is a finite dimensional inner product space. Tau is a linear operator on V. Tau is self-adjoint. Unfortunately, there's other terminology associated with this and in both cases, and it gets a little bit confusing. Tau is self-adjoint, also called Hermitian in the complex case and symmetric in the real case if tau star equals tau. I will try to stick to the term self-adjoint. It covers both cases, but sometimes I may not, and others will not always. So you need to know the terms Hermitian and symmetric as well. Tau is unitary, also called orthogonal in the real case, if tau is invertible and tau star equals tau inverse. And these operators are also called isometries. But to be perfectly clear, an isometry is a little bit more general than a unitary operator. An isometry is any linear transformation, tau, from V to W between any two inner product spaces that preserves the inner product. A linear operator, tau, on V, that is an isometry, is called a unitary operator. These operators have their matrix representations with respect to orthonormal bases are unitary matrices. They're square matrices. There are matrix versions of the two definitions I gave. Normally, I wouldn't need to separate the two because a matrix is a square matrix is an operator in our way of thinking. But there's one little kink, so that's why I did it. A square matrix is self-adjoint, again, also called Hermitian in the complex case, and symmetric in the real case if A star equals A. And A is unitary, also called orthogonal in the real case if A is invertible and A star equals A inverse. This we are familiar with. We've studied these a bit already. But there is one potential point of confusion, and that's why I separated out the matrix definition. The term symmetric, as it applies to operators and matrices in both cases, in these two definitions, applies to real operators and real matrices. But there are some situations in which a non-real complex matrix A has the property that it's equal to its own transpose. And we will encounter one such case later on in a theorem we're going to prove. A theorem you hardly ever see in the this level of linear algebra books. In fact, it's hard to find anywhere. And this situation will come up. We'll have a complex non-real matrix that's equal to its own transpose. So it is a situation that does occur, although it will only occur for us once, I think once. These matrices are also called symmetric. They're complex matrices equal to their own transpose. So the term symmetric, as it applies to a matrix, unlike an operator, applies also to complex matrices that are not real. So that's a little bit of a difference between the terminology for operators and matrices. The safest thing to do, that we will do, I hope, I'll try to do, and others will do and should do, is simply to use the terms complex symmetric matrix and real symmetric matrix to distinguish the complex case and the real case. And it's better to be clear on that than to be sorry later on and have to apologize for the terminology. I will probably use the term symmetric as I have given in the definition in the real case, and then use the term complex symmetric when I want to refer to a non-real, potentially non-real matrix that's equal to its own transpose. Since the properties described in the previous definition are preserved by unitary similarity, if a matrix is self-adjoint and any other matrix unitarily similar to it will also be self-adjoint, similar for unitary. If tau is a linear operator on V, then we also know from a theorem in chapter 6 that the matrix of tau star with respect to an orthonormal basis is the adjoint of the matrix of tau. So an operator is self-adjoint if and only if any matrix representation with respect to an orthonormal basis is self-adjoint. And if that happens, if tau is self-adjoint, then all of the matrix representations of tau with respect to orthonormal bases are self-adjoint. Similar statements can be made for unitary operators. So we have the usual picture. Here is tau, and here is the unitary similarity class that represents tau. If then tau, we've already seen that tau is normal if and only if all of these matrices are normal, in which case we refer to the whole class as being normal. Tau is self-adjoint if and only if one of these matrices is self-adjoint, and therefore they all are self-adjoint, and similar statement for unitary. If Z is a complex number, then of course its adjoint, which thought of as a one-by-one matrix, its adjoint is its conjugate transpose, which is simply the conjugate. Transpose does nothing. And so Z star does commute with Z. So we can think of a complex number as a normal one-by-one matrix. And that's kind of a tantalizing thought, because then we could stretch our imagination and think of, say, the family n sub m of all m by m normal matrices as a generalization of the complex numbers to dimension m. One doesn't want to rely on this too much because it is a bit of a leap, but it may be less of a leap than it appears right now, and that's what we're going to discuss. If we take this point of view, we might then seek to find the analogs within the normal matrices of a given size, for example, of certain important subsets of the complex numbers. What is the generalization of the real numbers to higher dimensions? What is the generalization of the positive real numbers, the non-negative real numbers? Also the numbers on the unit circle in the complex plane, the complex numbers of absolute value 1. So these are all interesting questions. And what we will see is that the connection between these various types of complex numbers and normal matrices, their higher dimensional counterparts, you might say, involves the eigenvalues of the matrices. So this is really, I think, a fascinating connection. In fact, what we will see is that a matrix A is self-adjoint if and only if its characteristic polynomial splits over the real numbers. This includes the case for if you have a complex matrix. It is self-adjoint if and only if its characteristic polynomial splits over R. Or put another way, if and only if the complex eigenvalues of A are in fact real. So a complex number is real if and only if you might say its eigenvalue, it is its only eigenvalue is real. So that's a tautology, I guess you might say. But at higher dimensions, a matrix, a complex, real or complex matrix, you just think of it as a complex matrix, is self-adjoint if and only if its characteristic polynomial splits, if and only if all complex eigenvalues are real. So that suggests to us that the higher dimensional analog of the real numbers among the complex numbers are the self-adjoint matrices. Those are the ones with real eigenvalues. We're also going to see that a matrix is unitary if and only if its eigenvalues have norm 1. So that would suggest that the complex numbers that lie on the unit circle, the ones of norm 1, generalize in higher dimensions to the unitary matrices. As to the analog of positive real numbers, we will see that those are the positive definite matrices, which we first encountered when we started to study inner product spaces. Remember that the Gram matrix of a finite dimensional inner product space is positive definite. Here's a full correspondence. Complex numbers correspond to normal matrices, or you might think of them as normal matrices as higher dimensional complex numbers. Real numbers correspond to the self-adjoint matrices. Numbers on the unit circle correspond to the unitary matrices. Positive real numbers correspond to positive definite matrices. Non-negative real numbers correspond to positive semi-definite matrices. I don't think we've discussed those yet, so let me give you the definition. It's very simple. Here's the definition of both positive definite and positive semi-definite. We've already seen that a matrix, it must be self-adjoint, is positive definite if this inner product, this is a standard inner product, AXX is non-negative with equality if and only if x is 0. A is positive semi-definite if this inequality holds without necessarily having the equality condition. Let me emphasize that the analogy between complex numbers and normal matrices and all the stuff we're talking about here is just a guide. It's just kind of fascinating. It would be dangerous to draw conclusions simply based on this analogy. When you move to higher dimensions, things can change. Things that might have been true in lower dimensions are not necessarily true in higher dimensions. So this is only a guide, not to be used in, these analogies are not to be used in proving anything. Okay, so let's take a look at the basic properties first of self-adjoint operators. And it's helpful to define the quadratic form associated with a linear operator tau. It's this function q sub tau mapping the inner product space V, upon which this is, I probably should have written here, tau in L of V. Mapping V to the base field, F. F is the base field. And it's defined this way. Q sub tau of V is the inner product, tau V comma V. There's a reason this function is called a quadratic form. And it is because if we have a matrix, like say for a square matrix, say for example a 3 by 3. This is an arbitrary 3 by 3 matrix. And we work out the quadratic form applied to an arbitrary vector, x, y, z. There's some algebra to be done, simplify the coefficients, and we get this expression. b1x squared plus b2y squared plus b3z squared plus b4xy plus b5xz plus b6yz. This is the most general homogeneous quadratic polynomial in 3 variables. A polynomial is homogeneous if all of its terms have the same degree. So to be quadratic and homogeneous means every term has degree 2. This is the most general such polynomial. To form terms of degree 2 from 3 variables, x, y, and z, we have x squared, y squared, z squared, then we have the various products, x, y, x, z, and y, z. This is also referred to as a quadratic form. But we are thinking of a quadratic form as a function. So this quadratic form will come up as we discuss the properties of self-adjoint operators. We've also seen that, and this was way back in chapter 5, that in a complex inner product space, an operator tau is 0 if and only if well, if and only if this is 0 for all vectors, v, little v, in the inner product space. So in terms of quadratic forms, it looks like this. Tau is 0 if and only if its quadratic form is 0. This does not hold in general for real inner product spaces. We used a little bit of a trick where we looked at qv of x plus iy, and so we needed the complex world to do that. But if tau is a symmetric operator, a real symmetric operator, then this does hold. So that's an added bonus of symmetric or self-adjoint operators in the real case. You can tell whether they're 0 by looking at their quadratic form. So here is the theorem giving us the basic properties of self-adjoint operators on finite dimensional inner product spaces. If we have two such, tau and sigma, both self-adjoint, then so is their sum. So is an inverse if the operator is invertible. So is the product if the operators commute. So is any polynomial in tau, provided the polynomial has real coefficients. We can also characterize complex operators, the self-adjoint ones, by their quadratic form. A complex operator tau is self-adjoint if and only if the quadratic form is real for all vectors v. So we were able to characterize, as we just went through, when an operator is 0 by its quadratic form. We can also characterize when an operator is self-adjoint by its quadratic form. Okay. And finally, the characteristic polynomial of a self-adjoint operator splits over the real field. So all complex roots of the characteristic polynomial are real. And then, of course, that would apply also to the minimal polynomial. As to the proof, I'm going to leave part 1 for you. For part 2, characterization by quadratic form, if tau is self-adjoint, then tau v inner product with v is equal to v inner product tau v. We move the tau to the other side of the comma. We would take its adjoint, which in this case is itself, and then use conjugate symmetry to move the tau back, basically. So tau vv is equal to its own conjugate, which means it's real. So the quadratic form is real. You understand what this means. The quadratic form is a function. What it means is that its codomain is real, or its image is real. Conversely, if the quadratic form is real, if tau vv is real for all v, then v inner product tau v is equal to, if we switch these two, we take complex conjugates, but this is real, so it does nothing. And now we can move tau to the other side. It becomes tau star. And because v is a complex operator, tau equals tau star. Okay, so it's important that this is a complex operator. That's required for the proof. For part 3, if tau is self-adjoint, then we've already proven this, as I said before, back in chapter 5, for the complex operators. So we can assume that the base field is R, that we have a real self-adjoint operator, or in other words, a symmetric operator. Of course, if tau is 0, the quadratic form is 0, but it's the other direction that we have to address. If the quadratic form for tau is 0, then that means that this inner product, where we have x plus y here in place of v, this is 0. We expand. We use the symmetry and the fact that q tau is 0. So tau y is 0, and tau x is 0. So we have these two terms, which I've reproduced here, and then this is the symmetry of the inner product. Let's see here. This one goes to this one. Those are commas, right? Yeah. Okay. And then tau can be moved to the other side because we're assuming tau is self-adjoint, and we have twice tau x y is 0, and therefore tau x y is 0. See, now x and y are arbitrary and they're not equal necessarily. So this will imply that tau is 0. So we have to be a bit careful here in keeping track of what's complex and what could be either complex or real in the statements of these theorems. For part 4, concerning the roots of the self-adjoint operator, there's two ways we could prove this. Generally, there's lots of ways of proving something, but there are two ways I wanted to point out to you because they're both of value. First, let A be a complex n by n matrix that represents tau with respect to an orthonormal basis. Then A is also self-adjoint. And if lambda z is an eigenpair for A, we're trying to then show that lambda must be real, then lambda zz, inner product z with itself, is inner product azz. Since A is self-adjoint, we can move it to the other, across the comma. This is equal to lambda z again, but now lambda's in the second component, so when you pull it out, it becomes lambda bar. Z is non-zero, so this is, so we can cancel the z's and we get lambda equals lambda bar. So lambda is real. As an alternative proof, we can appeal to the spectral theorem. The spectral theorem tells us that tau can be represented via an orthonormal basis by either a diagonal matrix, if the minimal polynomial splits, or a Schur block quasi-diagonal matrix, if the minimal polynomial doesn't split. In either case, the matrix representation is also self-adjoint because we're dealing with representations under an orthonormal basis. However, Schur block quasi-diagonal matrices are not self-adjoint because the Schur blocks, of which there must be at least one, is not self-adjoint. So tau must be represented by a diagonal matrix. But a diagonal matrix that's self-adjoint, it's equal to its own conjugate transpose must have only real entries on the main diagonal. In other words, all of the complex eigenvalues are real. So that's a very nice use of the spectral theorem in this situation. Certainly not necessary because a direct proof is so simple, but still it's good practice to apply sledgehammers even when you don't need them. Since this just as an aside note, that's not relevant to our discussion, but you will find it in other books. Since the minimal polynomial of a symmetric matrix, so a real symmetric matrix, splits over the reals, the spectral theorem implies that A is orthogonally similar to a diagonal matrix. This fact is often referred to in other books as the real spectral theorem. Remember, we had a discussion about the split between the complex and real cases. That's the way I think other books generally will handle this split that we have. We do it in terms of whether the minimal polynomial splits or not. Others will do it in terms of whether the base field is real or complex. So they will then have a complex spectral theorem and a real spectral theorem. Whereas we have a spectral theorem when the minimal polynomial splits and a spectral theorem when it doesn't split. So that's why you will see in other books something called the real spectral theorem. We don't need to call anything by that name because we don't make the division between the complex base field and the real base field. Now let's look at the properties of unitary operators. So V is a finite dimensional inner product space, and sigma and tau are operators on V. If they are unitary, then so is a scalar multiple of, let's say, tau, provided that scalar has absolute value 1. The product of unitary operators is unitary. The inverse of a unitary operator is unitary. We can characterize unitary operators. We've done this before. An operator is unitary if and only if it takes some orthonormal basis to an orthonormal basis. And if that happens, it takes all orthonormal bases to orthonormal bases. Remember, the unitary matrices are the change of orthonormal basis matrices. The determinant of a unitary matrix has absolute value 1. So it lies on the unit circle. And in particular, if A is orthogonal, so it's a real matrix. The determinant of A is real, then it's got to be either plus or minus 1 because it's real and it's on the unit circle. If tau is unitary, then the complex eigenvalues of tau have norm 1, which means the only possible real eigenvalues are plus or minus 1. Finally, the coordinate map of an orthonormal basis. So here's an orthonormal basis. Remember, the coordinate map sends vectors in V to their coordinate matrices. This is unitary. This actually follows directly from part 2 because the coordinate map sends this orthonormal basis to the standard orthonormal basis, and so it fits under part 2. I debated whether to include this in part 2 or not, but I separated it anyway. So I'll leave proof of part 1 to you. Part 2, as I say, we've already discussed back in chapter 6 when we talked about these unitary operators, unitary matrices. For part 3, we know that A transpose is the identity because, or A star is the identity because A star is A inverse. And we can take determinants. The determinant of the product is the product of the determinants. And the determinant of A star is the complex conjugate of the determinant of A. I'll let you think about that one. And so the determinant of A times its complex conjugate is 1, which means that norm squared is 1, so the norm is 1. For part 4, if tau is unitary and tau v equals lambda v, so this is the eigenvalue equation, then lambda bar, v inner product with itself, we can put one lambda in the first coordinate. We take lambda bar and put it in the second coordinate. It becomes lambda. And that is the inner product of tau v with itself. And since tau is an isometry, that's v inner product with v. And so lambda bar has to equal 1. In other words, the norm of lambda is 1. And I already discussed a minute ago the proof of part 5. So those are the basic properties of unitary operators.